Today's presentation is on polylactic acid and will be presented by Mary Rodriguez, Robert Madrid, and Terry Herrera. The course for which we are presenting is Chemi 361 Engineering Materials in the Chemical Engineering Department at NMSU, and it is instructed by Dr. Fudazi. Polylactic acid is a bioplastic derived from corn and sugarcane, unlike most plastics which are derived from petroleum. As you can see in the diagram, as you increase the purity of the PLA, the heat flow increases, therefore increasing the heat capacity.
Referencing the figure on the slide, I will talk about the basic manufacturing process of polylactic acid. In the US, PLA mainly starts out as cornstarch, which goes through a fermentation process where it becomes lactic acid. Once we have our lactic acid, we can then process it into lactide using either direct condensation polymerization or direct condensation in an azeotropic solution. The former results in a low molecular weight, the latter results in a high molecular weight. The lactide then undergoes ring opening polymerization where it becomes PLA. Before we can use it to create a final product, it must be put through a forming process that requires the PLA to dry. Note that PLA is sensitive to high relative humidity and temperature conditions. It must be kept sealed until ready to use. In the 1970s, PLA had high production costs, which limited its use to medical applications. As improvements were made to the process, production costs fell and it became more practical to manufacture PLA and extend its application outside of the medical field. Now we are going to talk about some advanced manufacturing techniques we use to create PLA products. Melt processing is the main method used for mass production of high molecular weight PLA. Next is injection molding, but we must note that injection molded PLA parts tend to be brittle due to the rapid cooling of the material during the shaping process. The last one we will talk about is cast film or sheet extrusion. This is used for things like food wrappings or protective films. There is good control of film thickness and uniformity during this process.
Just as with all other materials, characteristics of PLA or polylactic acid make it an ideal fit for some applications while not so ideal for others. These characteristics that limit its potential include low glass transition temperature, weak thermal stability, low toughness, and low ductility. Because of this, changes have been made to the manufacturing process as the ones listed above. These changes include adding modifiers, such as the one seen in the table, to help increase impact strength, flexibility, and barrier properties. Now, because of these modifications, the range of applications has increased widely. Today, nearly 70% of PLA is used as a packaging material for fresh foods, liquid containers such as cups and water bottles, and shrink wrap. Another common use is in the medical field, where PLA is used to make screws, pins, rods, and other materials that need to be degraded within 6 to 12 months. A final application is in 3D printing, and there is even some research being done to use it as a 4D printing medium as well. Because of its biodegradable character, PLA has the potential to massively reduce our dependence on petroleum-based plastics which are not environmentally friendly. Now, PLA, on the other hand, is extremely biodegradable, and as you can see, a PLA bottle will take only 80 days to fully decompose as compared to a PE plastic bottle, which can take years. Because of this, the marketplace for PLA is quickly expanding as seen in the graph. It is projected that the demand for biodegradable plastics will increase each year by 30%, and PLA will soak up the demand. In conclusion, PLA offers exciting potential as a plastic that can supplant our current petroleum-based plastics and in turn reduce our environmental footprint. Innovations in the manufacturing process and chemical processing of PLA is making this idea a reality.